Module 10.3, Complex Waves, Fourier Theory, Synthesis, and Analysis. We saw how standing waves can be created in strings and tubes. The frequencies of the waves were determined by the length of the tube or the string. For tubes, it also mattered if one end was open or not. Besides the fundamental, harmonics can also be produced. These harmonics are excited by the blowing of air, the buzzing of lips, the vibration of a reed, or the plucking or bowing of a string, or the vibration of vocal cords. The combination of these harmonics creates a complex wave. Since harmonics are integer multiples of the fundamental frequency, these complex waves will be periodic, repeating themselves at the period of the fundamental. In the early 1800s, the French mathematician Jean-Baptiste Joseph Fourier did some work where he theorized that any periodic waveform can be constructed from a series of simpler tones, a fundamental and its harmonics. This became known as Fourier theory. Taking a periodic waveform and determining what its component frequencies are is called Fourier analysis. This is a rigorous mathematical process, one that we will not attempt in this course. The process of combining harmonics together to form a wave is called Fourier synthesis. As we relate this to timbre, you can think of this as an analogy to cooking. Fourier analysis is like tasting food and trying to determine what the ingredients are. Fourier synthesis is like cooking or baking. Each of the frequencies are like the individual ingredients. You need to determine what ingredients, frequencies, and how much, their amplitude, to combine. This may help you understand why things sound different. If you and I both went home to make a pot of pasta sauce and then brought it into class, besides not getting any work done and having a great time, we'd have 2 pots of sauce. Both would be pasta sauce, but they would taste different because there would be a difference of ingredients, and for the similar ingredients, different proportions of those ingredients. Sounds are the same. A piano and a guitar playing the same notes will have the same frequencies, but the amplitudes of the frequencies will be different, causing the sound to be similar but different. Let's do a little cooking. Experimenting with Fourier synthesis. Let's take a sine wave and add it to a sine wave that's twice its frequency, its second harmonic. If we change the phase of the second harmonic, we can see that the wave shape changes. We can also change the amplitude of the harmonics and get yet a different waveform. As you would expect, changing the amplitude and number and combination of harmonics affects the waveform and the sound dramatically. Changing phase affects the waveform dramatically, but has only a slight effect on the timbre of the wave. We're now going to look at 5 different waveforms in detail. One is a simple waveform, and the other four are basic complex waveforms. A complex waveform is the result of combining two or more simple waveforms. When we talk about spectrums, we are always going to refer to relative amplitude. The math needed to come up with the actual numbers is complicated and not important for this course. So, for the 5 waveforms we will discuss, the amplitude of the fundamental will always be 1, and the harmonics will be fractions of 1. A sine wave is a simple waveform and the basis for Fourier theory. It has one frequency. Its period can be found by using the formula T equals 1 over F. A sine wave sounds like this. The first complex wave is a square wave. It's called that because it looks like a square. A square wave is made up of only odd harmonics, and the amplitude of each harmonic is equal to 1 over n, with n being the harmonic number. Its period can be found by using T equals 1 over F1. If you know its period, the fundamental frequency F1 is 1 over T. A square wave sounds like this. A triangle wave looks like the top of a triangle and is also made up of odd harmonics. It sounds like this. The amplitude of each harmonic is equal to 1 over n squared. Notice that the harmonics are much smaller in amplitude than those of a square wave. If you know the fundamental frequency, you can find the period by using T equals 1 over F1. If you know its period, the fundamental frequency F1 is 1 over T. A sawtooth wave looks like the teeth of a saw and is made up of all harmonics. Like the square wave, the amplitude of each harmonic is equal to 1 over n. And again, you can find the period using 1 over F1, and you can find F1 by using 1 over T. Here's what a sawtooth wave sounds like. A pulse wave is made up of all harmonics of a cosine wave. It sounds like this. Like the sawtooth wave, it has all harmonics. All the harmonics have an amplitude of 1. As with all these examples, the period equals 1 over F1, and F1 equals 1 over T. It is useful, when analyzing complex waveforms, to display the frequency information on a graph. As we said previously, the graph with that information is called a spectrum. It is often referred to as an FFT, which stands for fast Fourier transform. This is especially helpful when analyzing real-world waveforms. To review, Fourier's theory states that any periodic waveform can be constructed from a fundamental and its harmonics. Waveforms are affected greatly by the number and amplitude of harmonics as well as phase. Timbre is affected greatly by the number and amplitude of harmonics, but phase has a small effect on timbre. A sine wave contains just a single frequency. A square wave is made up of only odd harmonics, and the amplitude of each harmonic is equal to 1 over n, with n being the harmonic number. A triangle wave is made up of odd harmonics. The amplitude of each harmonic is equal to 1 over n squared. A sawtooth wave is made up of all harmonics. The amplitude of each harmonic is equal to 1 over n. A pulse wave is made up of all harmonics with equal amplitudes.